Hey everyone, welcome to this week's presentation on acceleration. Acceleration tells us how fast the velocity is changing. Just imagine that you're at Knoebels and you start rolling on the twister. Think about what this feels like as the ride starts to move. How does your body change as you go through the uphills and eventually you get to the top and you feel that feeling of going downhill? Think about the motion of a person's body as they're going through the twists and the turns of a roller coaster ride. So if you're like me, just seeing this on the video is enough to make me go, no thank you, this is not for me. But I can still figure out which directions my body would be going through all these turns. If I look at this spot here in the roller coaster, as the coaster cars start to go left, I know I'm going to get thrown to the right. As the coaster goes uphill, I'm going to be leaning back in my chair, and as the coaster's going downhill, I'm going to be leaning forward in my seat, trying to hang on for dear life. So let's connect that to something we've already learned. Think about this question. If Sam is walking north at a rate of 5 meters per second, did he describe his speed or his velocity? We know from what we've learned before that he's describing his velocity because he includes his direction. Speed and direction can change with time. That's the basic definition of acceleration. In the real world, if you were to go out on the street and ask someone what the definition of acceleration was, they would probably tell you it means, oh, that means something speeding up or going really fast. However, in the science world, acceleration means several different things. It's any change in velocity and how quickly that happens. So that means acceleration could be an increase in speed, a decrease in speed, or any sort of change in direction. So going up and then coming down, or going right, or going to the left, or going forward or backward. All of that is acceleration. An example of increasing speed might be a car speeding up when it sees the green light. Or decreasing speed is also acceleration. This is when the car sees the red light and comes to a stop. Or changing direction as the car goes around a corner, which can be at a constant speed, that is still known as acceleration in the science world. Acceleration measures how quickly speed and direction are changing. The speed of an object increases when acceleration is in the same direction as the motion. So we can accelerate forward, and that causes something to speed up, like pressing the gas pedal in the car. The speed of an object will decrease when acceleration is in the opposite direction as the motion. So this might be when someone steps on the brake in the car. That's going opposite to the direction of its motion, so the object's going to slow down. And the direction of the object changes when acceleration's at an angle to motion. So if there's a soccer ball coming toward you and someone kicks it from the side, the direction of the soccer ball changes, even though its speed may not. As we think about calculating acceleration, there are a few things we need to know. You can see the formula or the equation in front of you. We have to know the change in velocity. Because we need to know the change in velocity, that's the top part of this fraction. So we look at the final velocity minus the initial velocity. This gives us the change. So initial, just like the initials in your name, means the beginning. This is how fast something's going at the beginning of the formula, or the beginning of the equation. The final velocity is the speed it's going at the end. And when you take the difference between that, you're going to subtract. Once you've subtracted those, you divide that by how much time it takes to change that velocity, and that's where you calculate your acceleration. The units for acceleration, let's see if we can figure this out. Velocity in the metric system is measured in meters per second. Time can also be measured in seconds. So the units for acceleration are meters per second per second. And when we shorten that, it becomes meters per second squared. Think of acceleration like an interval. An interval is any number that you might be counting by, like you can count by ones, or twos, or fives, or tens. So if the acceleration is great, if you have a large acceleration, like you would be counting by tens, that means the object would be gaining or decreasing speed very quickly. So if the object starts out going 10 meters per second, in the next second, it's already going 20 meters per second, then 30, then 40, then 50. It would not take very much time to reach a very fast speed. An example might be like a rocket taking off. If the acceleration is slow or small, like counting by ones, the object's still going to gain speed, but it's going to gain speed over a much longer period of time. So if we're counting 1, 2, 3, 4, 5, it would take a lot more seconds to get up to 100. This might be like trying to ride your bike faster while you're going up a hill. You can do it, but your acceleration is much, much less when you're trying to speed up as you go uphill. So take a look at this animation. We have a red car, a green car, and a blue car. As you're watching, which one do you think accelerates the most? Which one changes its speed the most as it goes across the screen? Kind of ignore for a second that they all start at 0. If you watch closely, and if you try and watch each car individually, you'll notice that the blue car starts out slow but gains the most speed over time. The red car stays the same speed throughout, and the green car has an acceleration in between those two. So the red car has 0 acceleration, the green car has a smaller acceleration, and the blue car has the most acceleration. You can see also that if you are in a race, greater acceleration usually means you win the race. Let's look at the actual acceleration of the blue car. If we pretend that this is a number line down here on the bottom, we're going to track out the time of the blue car. So this says that the blue car travels for 4 seconds. And over that period of time, it starts at 0 meters per second. After 1 second, it's increased to 4 meters per second. 2 seconds, it's 8, then 12, then 16. If we fill this into our equation, initial velocity is 0 meters per second. Final velocity is 16 meters per second. 16 minus 0 is 16. Divided by the number of total seconds, which was 4, and we get an acceleration of 4 meters per second squared. So if we look at the number line again, it's like we're counting by 4s. So a couple of questions to think about. How could a car be accelerating if its speed is a constant 65 kilometers per hour? Remember, there are 3 ways to accelerate: speed up, slow down, and change direction. So if the car is turning, it's still accelerating. If an object has slowed down, how would its final velocity compare to its starting velocity? So if an object starts at 16 meters per second and slows down to 2 meters per second, which one's greater? In this case, its final velocity would be less than its initial velocity, and if you worked that out in an equation, that means its acceleration would come out to be a negative number. So here's where we bring in a meaning behind negative numbers as we look at math and science. Negative numbers now have a certain meaning when it comes to acceleration. A positive acceleration means the object sped up, but a negative number simply means the object slowed down. If you accelerate at 2 meters per second, remember that would be like counting by twos, how much would your velocity increase every second? Well, if we're counting by twos, that means you would increase your speed by 2 meters per second every second. And if you ended up at 6 meters per second, how many seconds would that take you? How long? That would take us 3 seconds if we were counting by twos until we got to 6 meters per second. I now want to look at graphing acceleration. We've looked at graphs for velocity. Now we're going to kind of compare those velocity graphs to what the line would look like if an object were accelerating. There are two kinds of graphs I want you to visualize. First, velocity versus time, so velocity on the y-axis and time on the x-axis, and distance versus time. It's the same acceleration. You can also find this on page 30 in your book. Same acceleration, but the lines will look different. So we'll start with velocity versus time. This is speed versus time. So if the object, if we are graphing the speed on the y-axis and time on the x-axis, what's happening to the speed as this cyclist rides downhill? It looks like his speed is increasing. So on a velocity versus time graph, acceleration would look like a straight uphill line. This would be positive acceleration. Negative acceleration would look like a straight downhill line. This also means that the acceleration is constant. We haven't even considered what if they speed up by 2 for a little while and then they speed up by 4. So it's possible for acceleration to increase or decrease while an object moves as well. If we change over to a distance versus time graph, you see how the line looks different. Now we're looking at how the distance on the y-axis compares to the time. So in this case, from 0 to 1 second, we've gone about 2.5 meters. From 1 to 2 seconds, we've gone another 2.5 meters. From 2 to 3 seconds, we've increased by 2.5 meters. And as we continue on, every time we increase our distance, that means our speed is increasing. If we were to figure out the speed at each point, we could take distance divided by time at each point, and we'd see that the speed was getting greater. So which line in this graph, notice it's distance versus time, which line represents an object that is accelerating? If you said the black and red lines, then you are correct. Black is growing a greater distance each second, so it's speeding up. Red is going less distance each second, so it's slowing down. Both of those represent acceleration. All right, I hope you understand how we see acceleration in the real world, and you can apply that to some new examples in the next assignment.